Welcome to the 3.5 through 3.7 quiz review, where we will be reviewing 3.5 derivatives of trigonometric functions, 3.6 the chain rule, and 3.7 implicit differentiation. What I recommend is to treat this as your own review, do the problems you feel like you really need to focus on, and then whatever you did not do well on, you can do the recommended assignment problems that I've put on the 3 assignments for these 3 sections. In problems 1 through 4, you'll be finding dy dx. And really the only problem that's different is number 3, which does involve the chain rule. Problem 5, finding the equation of a tangent line. Problem 6, dealing with the relationship between position, velocity, and acceleration. Problems 7 through 10, once again finding the derivative. These are a little more complex and all involve the chain rule. Problem 11 is a parametric equations problem. This is one a lot of us missed on the assignment. 12 and 13 are finding the derivative dy dx of implicit functions. And problem 14 is another tangent line equation problem, and asking us to write in slope-intercept form. Here are the worked out solutions. If you'd instead like to skip to the last part to just check the solutions first, go ahead and use the chapters feature to go to the very end. In problem number 1, we want to find dy dx. This one's pretty straightforward. The derivative of sine is cosine, and then the derivative of cosine is negative sine, so it's minus negative sine, so it'll be plus sine. And of course, we could also write this as sine x plus cosine x, since addition is commutative. In problem number 2, we have a product, and each one of the factors in the product, x cubed and sine of x, they each have the variable that we are differentiating in terms of in it. They both have an x in it, so we do need to use the product rule. Our u value is x cubed, and our v is sine of x. Those, of course, could be flipped, and we'll still get the same answer in the end, so long as you do the derivatives correctly. U prime, using the power rule, is 3x squared, and v prime, using the derivative of sine of x, that definition, is cosine of x. Then, of course, our product rule, is u times v prime first, so we'll have x cubed times the cosine of x plus v times u prime, so we'll write the 3x squared first. Again, in general, in a product, you want to write the trig function last. So we have that. This, again, on the quiz, if there's matching or multiple choice, things might be factored. So this is an acceptable answer. That is the derivative using the product rule. However, if you are asked to factor, or if something might be written in a factored way, the GCF of those two terms is x squared, and could also be written as x cosine x plus 3 sine of x. So either one is acceptable. In number 3, in order to find the derivative with respect to x, we see that we're going to need to use the chain rule. We need to use the chain rule because we're taking the cosine of a function that's more than just x, and therefore the derivative of this inside function here is more than just 1. So what we'll do is we'll just leave this negative 1/2 out in front, and the derivative of the outside function, which is the cosine of just the cosine of something, the derivative of a cosine of something is negative sine. And then we'll keep the inside function the same, and that doesn't change. The chain rule says we need to multiply by the derivative of that inside function. The derivative of that inside function using the power rule is 8x. Cleaning up, we see that we have 2 negatives being multiplied, so it'll end up being a positive. And outside we have half times 8x, which is positive 4x. So we'll have 4x on the outside times the sine of 4x squared. Number 4 can actually be written in a different way, and there are 2 different ways to deal with this. You could actually keep number 4 written like this and use the product rule because it is a product. However, I'm just going to rewrite that x to the negative second in the denominator, so as x squared. I'm going to do this just so I can highlight the quotient rule. Again, you could totally get the same answer using the product rule. I'm just not going to do it that way. So we have our quotient, and both the numerator and the denominator have x in it, so we do need to use the quotient rule. So we'll work up here. So the quotient rule says that to take the derivative of a quotient, we do low times the derivative of the high. The derivative of tangent is secant squared, and it's just x, so no chain rule necessary. So low d high minus high times d low. The derivative of the denominator is 2x, all over low squared, so x squared squared. Simplifying the numerator a bit, we'll have x squared secant squared x minus 2x tan of x all over x to the fourth. So this is a perfectly acceptable answer. Again, things might be factored out a little bit and simplified. Therefore, in the numerator, we can actually factor out an x, since that's the GCF in the numerator. So we'll be left with x secant squared x minus 2 tan of x, and that's all over x to the fourth. Now that can be simplified a bit, as an x to the first can cancel. So this x to the first and then one of the x's down here can cancel. So our final answer can look like x secant squared x minus 2 tan x all over x cubed. Number 5 is a tangent line problem, and we have the same directions every time, the same, steps every time to find the equation of any line. We need a slope and a point, and so we don't quite have either one yet. So what I'm going to do first is find the coordinate point, and we know that our x value is 3 pi over 2. But what's our y value? So in order to find the y value, I'm going to plug in 3 pi over 2 for x into our equation to find y. So we'll have 2 times the cosine of 3 pi over 2 minus 5. The cosine of 3 pi over 2 is 0. Use a unit circle if you need to see why that is. So we have 2 times 0 minus 5. So our y value ends up being a minus 5. So now we have our point. Now we need to find our slope. In order to find our slope, what we're going to do is take the derivative, dy dx. That'll give us our instantaneous rate of change or slope at any point. So the derivative of 2 cosine is negative 2 sine of x. And the derivative of minus 5 is 0 since it's a constant. Then we need to find our value of our derivative when x is 3 pi over 2. And so we'll plug in negative 2 times the sine of 3 pi over 2. The sine of 3 pi over 2 is negative 1. So our slope is 2. So we have our point and we have our slope. Therefore, we can use point-slope form. When we do this, we'll have y minus negative 5 equals our m, our slope, times x minus the x-coordinate, 3 pi over 2. To get this solved for y, we can distribute the 2 through, depending on how the question's asked. So if you're asked to put it into slope-intercept form, or if that's what the multiple choice solutions look like, you sort of have to go from there to see how to write it. But I'm going to distribute the 2 through, since that's not too algebraically difficult. 2 times the 3 pi over 2 ends up just being 3 pi. And then we want to subtract 5 from both sides, so we'll have y equals 2x minus 3 pi minus 5. And we can't really, normally you don't want to simplify pi just because it's a crazy decimal. In number 6, we have a classic position, velocity, acceleration problem, and so we just need to understand the relationship between them. If we take the derivative of position, we end up with velocity, and then if we take the derivative of velocity, we end up with acceleration. So moving from position straight to acceleration would just mean we need to take the second derivative. There's a few different ways to look at that. What we want to do is find the velocity when time is pi over 2. So for part A, what we need to do to find the velocity equation is take the derivative of the position equation. So s prime of t is velocity. And then taking the equation here and finding its derivative, the first term, we'll use the sum and difference rules because it's just a difference. So the derivative of 4 cosine t is negative 4 sine of t, and the derivative of minus 3 sine t is minus 3 cosine t. So we have the velocity function, and now we need to find the velocity at pi over 2. So I'm going to plug pi over 2 in, just kind of in my head here. So the sine of pi over 2 is 1, and then the cosine of pi over 2 is 0. So the sine of pi over 2 is 1, meaning the first term is negative 4, and our second term goes away since the cosine of pi over 2 is 0. So the velocity at pi over 2 is negative 4. We do not have units in this problem because I forgot to write them, so we're just going to leave it as negative 4. For part B, we need to find the derivative of velocity, or the second derivative of position. So I'm going to write this out real fancy. So the second derivative of position equals the first derivative of velocity, which is how we find acceleration. So we're essentially finding the derivative of our velocity function here, kind of using the same methods. So the derivative of this first term here, negative 4 sine of t, would be negative 4 cosine of t, and the derivative of the second term, minus 3 cosine t, is plus 3 sine t. This is really a problem where you just have to be careful with your positives and negatives. All right, now part B wants us to find the acceleration at pi over 2. So we need to find a of pi over 2. So once more, we can do this in our head. The cosine of pi over 2 is 0, while the sine of pi over 2 is 1. So this term goes away, and this term ends up being 3 times 1. So our acceleration is 3. Again, lack of units because I forgot to write them. So basically, these ones are pretty simple. They are testing your knowledge of understanding the relationship between these three ideas of something in motion, and also usually they deal with trig functions. Let's take a look at problem 7. We want to find the derivative of this product, and so that means we need to use the product rule. So our u can be the tangent of 3x squared, and then our v will be the cosine of 2x. Therefore, u prime is going to be secant squared of what's inside, that inside function, times the derivative of the inside function using the chain rule. So the derivative of 3x squared is 6x. Then v prime is also using the chain rule. The derivative of cosine of 2x would be negative sine of 2x and then times 2. So I'm going to clean up the u prime and the v prime with just how they look. So u prime, I'm going to write the 6x first. And then v prime, we'll write the negative 2 out in front. So just cleaning up how we're writing u prime and v prime before we finish the product rule. So our product rule is going to be u times v prime. So I'm taking u times v prime. So we'll have a negative 2 written out front. And then we can write both of the trig functions there being multiplied. So we'll have u times v prime. You can write the tangent function first or the sine function first. It does not matter since they're being multiplied. But what does matter is that that negative 2 goes out in front of that whole term. So this is u times v prime written appropriately. Then we want to add v times u prime. So cosine of 2x times 6x secant squared of 3x squared. So once again, for the same reason that 6x goes out front, and really the other way that you write stuff, it does not matter the order, since multiplication is commutative. Now, this is pretty messy looking. Could it be simplified? Sure. Well, actually, could it be simplified? It doesn't actually look like it really could. I guess the only GCF between these two terms is just a 2. So you could factor a 2 out. I'm just going to leave it be. In problem number 8, I'm actually going to rewrite this as what's under the radical, our radicand, raised to the 1/2 power, so we can clearly see the power rule a little bit better. To find the derivative of something to the 1/2 power, we use the power rule by bringing the 1/2 out in front, and then raising that something, in this case 10x minus 6x squared plus 3, to 1 less than 1/2, which is negative 1/2. Now, because what's on the inside is not just x, we do have to use the chain rule, meaning multiply by the derivative of the inside here, this inside function, this quadratic trinomial. So the derivative of that inside piece is 10 minus 12x. Simplifying this, this is a fraction, and what's in the numerator is the 10 minus 12x. The denominator has a 2, since that 1/2, and this is raised to the negative 1/2, meaning it's a square root in the denominator. Now I do want to point out that in the numerator we can actually factor a 2 out. So I'm going to rewrite the numerator factoring a 2 out of that 10 minus 12x. So we can factor a 2 out of the 10 minus 12x and we'll be left with this. The reason I did that is so these 2's could cancel. So what we're left with is 5 minus 6x over the square root of 10x minus 6x squared plus 3. For number 9, I rewrote the square root that's in the denominator as the 4x minus 7 to the negative 1/2. So we could clearly use the power rule. So we actually don't need to use the product rule here, because even though we do technically mathematically have what is considered a product, this factor right here of 7 does not have an x in it. So if you do end up using the product rule, you will get the same result at the end, but if you make 7 your u prime ends up being a 0. And therefore, when any part of the product or quotient rule is a 0, like the derivative, it wasn't necessary in the first place, but it'll still get you where you need to go. So that's just my little PSA. All right, let's do the power rule. I always want to confuse power and product when I say it. All right, we're going to bring the negative 1/2 out in front and multiply it by the 7, giving us negative 7/2. The 4x minus 7 then gets raised to 1 less than negative 1/2, which is negative 3/2. And then using the chain rule, we have to multiply by the derivative of the inside piece here, which ends up being just 4. So on the outside, we can multiply negative 7/2 times 4 over 1. 4 over 2 actually end up canceling to just a 2. So we end up getting a negative 14 out in front of our derivative. And then raising something to a negative means it's in the denominator. The denominator of that negative fractional exponent is a 2, meaning it's a square root. But the 3 in the numerator means that that ends up being cubed. Now that cubed can go like on the outside, just like you see, or if you end up writing the cubed on the inside, it would have to look like that with parentheses. So normally we just write it on the outside like that. For problem number 10, what you can do is actually rewrite sine to the 5th of x as sine of x, the whole thing raised to the 5th. Note that the x is not raised to the 5th. It's the sine of x, and that's why we put the 5 here. All right, so this actually is power rule and then chain rule. So we are taking the power rule because it's something raised to the 5th, which means we deal with that as 5 times that something and then raise it to 1 less. So we just use the power rule. Then we do need to use the chain rule because that something, that inside function, is not just x, it's sine of x, and so it has a derivative that's more complex than just 1. So we need to multiply by the derivative of what's on the inside. The derivative of our inside function, sine of x, is cosine of x. So then writing this as a final answer, that 4 ends up going back here. That's just how we cleanly write it. And the cosine and the sine to the 4th could have been written in either order, but the 5 should go out front. I'm sure a lot of us are going to be watching this one because it is a parametric equation problem. And a parametric equation just means that we have a third variable, a lot of times t for time, that both x and y are independently defined by. And we want dy dx in terms of t, but how do we get there? We have a separate x and a separate y. The main idea behind this curve that is parametrically defined is that in order to find dy dx, we need to first find dy dt, and divide it by dx dt. The dt's end up canceling, and that's why it gives us dy dx. So we need to separately find dy dt and dx dt. So we'll do this first part in light blue to find dy dt. So we are finding the derivative of y with respect to t. So the derivative of 1 is 0, and the derivative of sine of 4t is cosine of 4t times 4 using the chain rule. I'm going to put the 4t in parentheses. All right, so we found dy dt. That's great. The next thing we need to do is find dx dt. Oh, that'll go in the denominator of our eventual fraction. So dx dt is the derivative of x with respect to t. So the derivative of 3t is 3. And the derivative of minus tangent of t is minus secant squared of t. Okay, cleaning up this problem, in order to find dy dx, I just rewrote this part here so it looks a little more organized. We want to put dy dt and divide it by dx dt. So we have dy dt right here. Dy dt is 4 cosine of 4t. And then dx dt is right here, 3 minus secant squared of t. Now we can't really clean anything up, therefore that ends up being our final answer. For problem number 12, we want to find dy dx for this implicitly defined equation or function. Again, implicit just means that both x and y are like mixed in together, or whatever two variables. It's not simply like y equals something in terms of x. In this case, we could actually get this to look explicit by solving for y, but we can just directly find dy dx from here. So in our first term, xy, this is a product, and I'm going to write out our product rule here. So our u is x, our v is y, our u prime is 1 because it's with respect to x, and then our v prime is 1 dy dx. It's the derivative of y with respect to x. So let's go ahead and write out that first term here. Its derivative, because we're taking the derivative with respect to x. So we have u times v prime, so it's x times dy dx, plus vu prime, which is just y. Then, next, we want to take the derivative with respect to x of minus 3y, which is going to be minus 3 times dy dx. Then the derivative of 15 with respect to any variable, in this case x, is 0. It's a horrible 0. There we go. Just 0. So now what we want to do is solve for dy dx, and to do that we want to keep all the terms with dy dx in it on the left, but move all the terms that don't have dy dx in it to the right. So the only term without dy dx in it is y, so we're going to subtract y from both sides. So we'll be left with this term and this term, both with dy dx in it, which we want to get by itself. Now the reason that we moved all those terms with dy dx in it to the left is so we could factor out dy dx. When we factor out dy dx from both of these terms, we're left with x minus 3. Then we can divide both sides by x minus 3 to get dy dx by itself. And therefore, we end up getting dy dx equals y over x minus 3. So our derivative is also an implicitly defined equation. This equation is also implicitly defined. It would be very difficult, but not impossible, to get it as y equals. So what we want to do is take the derivative of each term with respect to x. So our first term, using the power rule, is pretty simple. Its derivative with respect to x would be 12x cubed. Then our second term is actually a product. So I'm going to write out our product rule. So we'll do u and v. Our u is 2x squared, and our v is y. So our u prime, the derivative of u with respect to x, is 4x, and v prime, the derivative of y with respect to x, is 1 dy dx. So writing this out, we'll have minus all of this, minus u times v prime, plus v times u prime. And then we're going to keep going. So I'm going to bring that 12x cubed down. Then we want to find the derivative of 1, which is just 0, so it'll go away. Then it's going to be equals 5y, the derivative rather of 5y with respect to x, which is 5 times dy dx. So this problem has a little bit more going on. We need to distribute that minus sign through. So we'll have 12x cubed minus 2x squared dy dx minus 4xy equals 5 dy dx. So I'm going to do a little bit of algebra to get the terms with dy dx on the left. So I'm going to subtract 5 dy dx from both sides, and then move these terms without it to the right. So I have done all that moving around. We subtracted this, so that's why it's negative over here. This term stayed, where we subtracted 12x cubed and added 4xy. All right, now we want to factor out the dy dx, and what I'm going to do is, because they're both negative, I'm going to factor out a negative dy dx instead, and so we'll be left with 2x squared plus 5 equals still this side. Then what we can do is divide both sides by a negative 2x squared plus 5. So to write our final answer, and those negatives, that looks like plus signs, but they canceled out. So we're left with dy dx equals, and this negative here can just go out in front of our entire fraction to make it simpler. So it's negative 4xy minus 12x cubed over 2x squared plus 5. Yes, there are many alternate ways to write this final answer, and therefore, one like this may or may not be multiple choice. This one's a little bit more complicated. We're going to end this quiz review with a problem, again, about a tangent line. Love those tangent line problems. We do have an implicitly defined function, so we do need to find the derivative, dy dx. We actually already have our point, which is great. So to find dy dx, we need to take the derivative with respect to x of each one of these terms here. So we have x minus 3 quantity squared. That means we're going to use the power rule, so we're going to bring the 2 out in front, and then have x minus 3, and then raise it to the first power, multiply by the derivative of the inside, which is just 1. Then we're going to take the derivative of plus y squared with respect to x, so we're going to have plus 2y dy dx equals 0, the derivative of 10 with respect to x. And I actually meant to just write d dx here, since we're taking the derivative of each term with respect to x. All right, so now we want to solve for dy dx. I'm going to multiply this 2 through, which actually, maybe that's not necessary. Let's actually subtract that from both sides. So we're left with this when we subtract it. Then we'll divide both sides by 2y to get dy dx by itself. And so our dy dx, the derivative equation, ends up being negative times the quantity x minus 3, which you could totally multiply the negative through if you wanted, divided by y. Now to find our derivative at our point, 4, 3, we have to plug in 4 for x and 3 for y. So our derivative, at that point can look like this. So we'll have negative and then 4 minus 3 all over 3. So it's negative 1/3 is our derivative. Then to write in slope-intercept form, it's going to be y minus our y-coordinate, which is 3, equals our slope, negative 1/3, times x minus our x-coordinate, which is 4. Then solving for y, And getting it in slope-intercept form will look like this to distribute the negative 1/3 through. Then we have to add 3 to both sides. 3 is really 9/3 to get a common denominator. So we'll have y equals negative 1/3 x plus 13/3. Welcome to the quick solutions. Here's problems 1 through 4. Problems 5 through 8. And 9 through 14. Please note that number 13, there's a lot of negatives and positives around this problem, and if you want to see how I wrote it in this specific way with the negative out front, take a look at the quick solutions. Chances are if you have these terms but a few are negative and like flipped around, you still have the correct final answer. I'll end this review by saying good luck on your quiz. However, you make your own luck based on how much effort you put in and how prepared you really make yourself for the quiz. So if you went through this and did a great job, that's awesome. You should be well prepared. If there were a few that you were pretty shaky on, I recommend going back through them, really understanding, attending office hours, and or taking a look at the recommended book practice problems on the 3 assignments from these sections. And now I'll say it, good luck.